All right, this is the wave equation, utt equals to c squared. And the previous wave equation that we've solved was a one-dimensional wave equation where it looked like utt equals to c squared uxx, right? That was the one-dimensional wave equation. And we solved this for the infinite real line, which gave us the D'Alembert formula. We also solved it for the case where two endpoints were tied, like a string vibrating. That we solved using separation of variables. Now, in the second dimension, dimension 2, you could have something that looks like this, which models a vibrating two-dimensional object. Okay? And one thing you could do with this would be to think about a rectangular drum. So what's a drum? You have some frame and then you put some dead animal skin, something like that, right? And then you beat it and then it gives you some sound, right? So if it's a rectangular drum, then you can solve this one with some boundary conditions. Usually, because drums are fixed at the end points on the frame, you have the boundary conditions at 0, and you can certainly solve this using separation of variables. We will not do this one because it doesn't really give us anything new. It's just exactly like the first group case. What's more interesting and actually more practical is usually drums look round, right? You have more round drums than rectangular drums. So if you have a round drum, and then you're trying to beat it so that there's some vibration on this skin, right? Then you have to use a different form of the Laplacian. This one's called the Laplacian, but you have to change this into polar coordinate system. That's why I have this weird looking thing. That's the Laplacian written in polar coordinates. And you've done some homework and you watched my video deriving this. It takes a long time.
They're equivalent, right?
Huh?
Are they equivalent?
What is it? Oh, yeah. So the value of the Laplacian will be same at a given point, whether you use the rectangular or polar. They'll give you the same value. Yeah. Okay. So that's what you have, and this thing is saying that we're doing it for the case when the radius is 1. So this drum head has radius 1, and it's tied down, so it's 0. That part doesn't vibrate. And initially at time t equal to 0, it has some configuration, and it will also have the velocity. Notice that because this is a second order differential equation in terms of time, you need to provide two initial conditions. The value of u at time 0 and the value of the velocity at time 0. So those are given, and then there's some extra conditions that we've dealt with when we were solving Laplace equation of this, which was that you have some continuity condition for the theta, because there's a cut where theta equals to pi and theta equals to negative pi, and then when there's a transition from negative pi to positive pi, you want such that the values agree, so it's a continuous function. So u r pi t has to agree with u r negative pi t, and then u of r u in the theta direction. If you differentiate the theta direction, u r pi t should also still agree with u theta r negative pi t, so that the slopes agree as well in the radial direction. So that these two conditions make sure that you have a smoothly varying function in the radial direction, which agrees with our usual intuition of what a waveform would look like on a drum, right? So since we've discussed this part when we were doing Laplace equation, I will erase it for now, but we'll later make use of it somewhere in the discussion. Okay, so right now I don't intend to solve this fully. We will revisit this, but I want to stop where we get the Bessel's equation. So I'll call this part 1. And then after we find the Bessel's equation, then we're going to talk more about Bessel's equation, and then later somewhat revisit that, come back to this one, and we'll solve for it, right? Okay, so we're going to do separation of variables, the usual one, right? So you have, well, for now, let's just write down u as a function of t times a function of, let's try v of r theta. So that if you plug this into the left side, this will be, the left side will be t double prime of t times v, r theta, equal to, and we're just going to call this as Laplacian of u, where this Laplacian is only being acted on the r and theta variable. So if you plug this on the right side into u, then c squared will still be c squared, and t of t would be unaffected by Laplacian of u, because these derivatives don't do anything to t, right? So t of t wouldn't change. And then it will be the v that will be getting the Laplacian operated upon. Right? And then, as usual, when we do the separation of variables, we divide both sides by, in the heat equation I said kxt, right? But here it's, instead of k you have c squared, so we divide by c squared tt v r theta. So it's c squared tt v r theta. And the result is that these will cancel out, and these will cancel out, these will cancel out. And then you have t double prime of t over c squared t of t equal to Laplacian of v over v. Okay. Now, the left side is a function of t only. The right side is a function of r and theta. How can a function of t equal to a function of r and theta for all values of r, theta, and t? How can that happen? If it's yeah, if it's equal to a constant, right? Okay. So we're going to set it equal to a constant, and the choice of my choice of constant will be negative mu squared. And that requires a bit of explanation why I can put a square there, which means if I have mu squared, that means this mu squared is a positive number, right? So I owe you that explanation a little bit. So let me do that first. But in order to explain that, I have to solve for t and then solve for v as well. So let's first think about this part. This equals to negative mu squared. What does that mean? That means t double prime equals to c squared, actually, minus c squared mu squared t. And you move this to the other side, you get t double prime plus c squared mu squared t equals to 0. Which is what we are going to solve a bit later. So let's save this. On the other hand, if I solve this by first multiplying by v and moving it to the left side, we get Laplacian of v plus mu squared times v equal to 0. this is a case where you have, let's see, this is a case where since your u is 0 on the boundaries for all time, you don't want, so this will be 0 at 1 comma theta, right? On the boundary of the disk, it will be 0. You don't want this to be 0 because if this is 0, then you have a trivial solution. You don't want trivial solution. So it must be that this has 0 on the boundary. So this equation has the following form. You have a disk of radius 1, that's what we were working on. And we're setting V as 0 on the boundary. And you're trying to look for non-trivial solutions that would satisfy this. Is it okay? Yes?
T cannot be bounded, so it's
T of t cannot be 0 because if it's 0, then u would be trivial. And we're looking for non-trivial solutions. As always, when you do separation of variables, you're looking for building blocks to use to make up the solution, right? So having trivial solutions doesn't add anything to your knowledge. Okay. So if you have a boundary condition of some kind, and you have a Laplacian of some function plus some value equals to of times v equals to 0. This is again another form of eigenvalue eigenfunction problem. It's just that we've only dealt with eigenfunction problems in 1D, which we call Sturm-Liouville. This one is a two-dimensional one, and the one for the Laplacian is called the Helmholtz equation. And it's another eigenvalue problem. And if you recall, when we did y double prime plus lambda y equals to 0, I said, well, it never happens that lambda is negative. Lambda is always 0 or positive. Right? Same thing happens over here as well. Okay? But here we could just explicitly try the case when lambda is negative and show that it doesn't work. But here, it's really hard to do that. So let me give you an intuitive explanation, just like how we were doing it as before. Okay? All right. So think about the. So what I want to do is. What I want to do is that if you just set v plus some constant a v equal to 0, then a has to be positive or 0. That's what I want to show. Actually, it has to be strictly positive, because if it's equal to 0, then you have the Laplacian of v equal to 0, and our condition is such that the boundary value is of 0, right? So we know that the unique solution is 0 everywhere. So you're forced to have a non-zero case. So we definitely know that 0 is not possible. But let me try to explain what happens if this is negative. So why a cannot be negative. Well, it cannot be negative because suppose you're looking for a non-zero solution, right? You're looking for a non-trivial solution. Then that means either v would have a positive value inside or negative value inside, right? If it's in the positive case, then it must mean that you have a non-zero maximum value inside. Okay. So let's think about what happens if v is positive. If v is positive inside, if it's non-trivial, it has to be either positive at some point or negative inside, right? Negative at some point, right? Do you agree? If it's not all 0, it's either plus or minus. Okay? Let's think about the case when it's plus. then you must have a positive maximum inside. Okay? If you have a positive maximum, what happens? Second derivative must be negative, right? The Laplacian must be negative because it's a concave down thing. So if you differentiate twice in the x direction plus twice in the y direction, add them up, they're both negative, so this will be negative. But look what happens if this is negative, and we're saying this is positive at that point of maximum, right? Then what sign should this be? This can't be negative. Do you agree? Then they're both negative and you can't add to 0. So that doesn't make sense. All right? So that's the case. Now, what if b is less than 0? Then you know that you have a negative minimum inside the domain. By the way, for math majors, you learn this as if you have a closed disk that's called a compact domain, and any continuous function over a compact domain will either have a maximum or a minimum, right? It always have a maximum. It always has a minimum inside the domain. That's something that you learn in. Yes?
Why it cannot contain both maximum and minimum?
You could, but either way, if it has a positive maximum, you have a contradiction if you say A is negative. If it has a negative minimum, if it's a negative minimum, what do we know about the Laplacian? It's a minimum, right?
Positive.
Laplacian must be positive. Yeah? Second derivative in the x direction, second derivative in the y direction, they're both concave up, so it must be positive. So you have positive, but the value at the minimum will be negative. So this has to be positive. It can't be negative, it has to be positive. So you can kind of see why I said I said this value should be positive, and I'm writing this as mu squared. Is that okay? It has to be mu squared, or else the geometry doesn't make sense. Okay. All right. So that was a fine point. That's usually not explained well in the textbooks, but I just wanted to make sure that you understand why people do that. Right? Okay. So once you're convinced with that, let's now redo this a little bit. Let's now restart this. With u equals to t, r theta, r of r, theta of theta. And by the way, we're basically restarting the whole proof. The only thing that came out of this discussion was that at some point we have t double prime over c squared t, and we're going to let it equal to negative mu squared. That's the only thing. Okay. All right, so let's do this over. Plug this into both sides. Now you have second derivative with respect to t, so it's t double prime of t, r of r, theta of theta, equal to c squared. If you're doing second partial with respect to r, only this is going to get differentiated twice. By the way, let's not write down t's and r's because it's going to be taking too much space. I'll just write down t double prime r theta equals to c squared t r double prime theta plus 1 over r t r prime theta plus, okay, let me see if you're paying attention. What would this be then? The last one. 1 over r squared u theta theta. What should I write?
1 over
R squared times
TR
T R
theta prime
theta double prime.
double prime.
Yes. Okay. So we have that. Now what should I divide both sides by?
1 over squared TR theta.
Yeah, C squared T R theta.
not include R squared? 1 over R squared?
No, you don't, because this one doesn't have 1 over R squared. You don't want to include that. So you do that, then R theta cancels out. All the t's cancel out. C squared cancels out. And here's what we have. We have t double prime over c squared t equal to, this over this is like r double prime over r. This over this, thetas cancel out and you get 1 over r times r prime over r. And then this over this, r cancels out and you get plus 1 over r squared theta double prime over theta. Right? R canceled out and you have theta double prime over theta. You still have 1 over r squared. Okay? And from the previous discussion, what do we let this equal to? Negative mu squared. And now this splits into 2 equations. One is t double prime plus c squared mu squared t equals to 0. The other one is if I multiply, so this time I have to multiply by r squared. Oh wait, just a minute. I have to be careful here. For this second one, I'm not going to multiply by r, but I'm only going to multiply by r squared both sides. So I get r double prime over r times r squared plus r times r prime over r plus theta double prime over theta equal to negative mu squared r squared. Okay? So I still have to say something equals a constant, but what's our strategy? We put functions of one variable only equal to another function of another variable, and once you set them equal to each other, you say, the only way this could happen is it's equal to a constant, right? So how do we make that argument here? What should we do in order to make that argument? Any ideas? Move what?
Let the theta term to
the right side, okay. Yeah. That's it? That's all you need?
And equals to another constant.
So then you move then the mu squared.
Mu squared r squared should be on the left side. Okay. So what you need is r squared capital R double prime over capital R plus r times capital R prime over capital R plus mu squared r squared equal to negative theta double prime over theta. And now the argument goes that the right side is a function of theta only, right? Whereas on the left side, these are functions of r. See, I don't want this to be on the right side because then the right side will have both theta and r. Then you can't make that argument. By moving it to the left side, now you have left side only a function of r. This doesn't have any theta dependence. Whereas on the right side, this doesn't depend on the value of r. So now you say it's equal to a constant. So you set equal to lambda. Okay. Now, as usual, you want to set equal to lambda, not negative lambda, because then, yeah, you would, if you solve for theta double prime and move things around, then you get theta double prime plus lambda theta equal to 0. Right? And then here comes that argument about the theta, right? Theta has to be periodic around pi and negative pi, right? And their derivative has to be the same as well, right? And we solved this in the Laplace disk case. Do you remember what the eigenfunctions were for that periodic boundary conditions?
A equals sine plus b sine.
Yes, yeah. So the solution, the eigenfunctions were theta equals to a cosine theta plus actually n theta, cosine n theta plus b times sine n theta. So those were our eigenfunctions with eigenvalues lambda as n squared. Okay? So slowly we are getting some results here. So up till here, nothing seems to be coming out of our discussion, but now we have a real result, right? We know that the only kind of non-trivial solutions you can have are the cases where theta are a cosine n theta plus b times sine n theta, and lambda will be n squared. And because lambda is n squared, now you can plug them back in over here and then set it equal to this one. This equal to that, right? So we have r squared, r double prime over r plus r capital R prime over r plus mu squared r squared equal to n squared, but I can move the n squared to the other side and put it minus n squared equal to 0. And then this doesn't look like a nice looking differential equation, but now what we do is we say r squared r double prime. We just multiply the capital R all the way across so that all the denominators capital R goes away. So this is the differential equation you get. And this one already looks a little bit familiar, except that
For sure.
Can we plug in R2?
oh, no. That's a good question. All right, so you're referring to the Laplacian equation case where we didn't have this, and
right.
that was called Euler-Legendre equation where r to the kth power is a solution, right? But the difference here is that now we have this term, and we also know that mu is non-zero. So
Can we use the signal?
that we need to have power series solutions. Yeah. So that's exactly what we have to do. But to make it look more familiar to something that I introduced, let's do this change of variables. So let's say x is equal to mu times r. Okay? If x is mu times r, then if you have r prime, which is dr dr, and if you want to rewrite this in terms of differentiation by x, then you need this by the chain rule, right? No, sorry, dx over dr. Right? Is that okay? So, see, this r prime really means you're differentiating with respect to r. And in order to rewrite this equation in terms of differentiation with respect to x, you have to figure out what to do with this, right? But what is dx over dr? What is it?
It's just
Mu.
mu.
Right? So if you differentiate x by r, it's just mu. So it's mu times dr dx. And then, for the same reason, r double prime will be doing this again. So you get another mu, so it will be mu squared dr dx. So if you first rewrite these in terms of d dx, you get r squared mu squared second derivative with respect to x plus r times mu times the first derivative with respect to x plus mu r squared minus n squared r equal to 0. And now you can see that mu times r, since that's equal to x, it's like this. You have x squared, and let's change the meaning of r prime. So this time it's the derivative with respect to x, okay? And mu times r is x, so it's x times r prime plus x squared minus n squared times r equal to 0. And in a couple of lectures ago, I explained something called Bessel's equation. That's exactly this one, except that over there I was using x and y, right? X squared y double prime plus x times y prime plus x squared minus n squared, y equals to 0. And that's called the Bessel's equation of order n. Okay? And how did we solve this? We used
Y equals to sigma.
sigma of something, right? We had power series solution. Okay? And what really happens is that this solution has two solutions. So let's first talk about this y. So y would be, one solution will be what we call Bessel's function of the first kind, Jnx. But it's a second order differential equation, so there will be a second part of it, right? So you have C2, and the second solution is called y and x. Now this second solution happens to have a singularity at 0, so it doesn't behave well, so that's not good. On the other hand, this one will have a finite value at 0, so this behaves well. So because when drums are vibrating, it doesn't take on infinities, right? So this will be immediately taken out as non-physical, and we will only get this one, right? So in this context, you'll be writing r, right? But then also x was what? X was mu r. So you really have r of r, capital R of small r, is C1 Jn mu r plus C2 Yn mu r, where this one is called the Bessel's function of first kind, and this one is called the Bessel's function of second kind. Okay. So this is where I want to stop part 1, and once we learn more about the Bessel functions, we'll revisit this one and finish until the end. The interesting part would be, well, not that interesting, but I'll present to you some facts about the Bessel function so you can gain some more understanding of